and welcome to Serbia. We are at the National Serbian Weather Station, Niš Fortress, Niš, Serbia. We'll be watching a robotic balloon launch, which is going to be coming from this green container here at 15 minutes after the hour. And I will wait to let people trickle in for the next half hour, and near the top of the hour, we'll start actually chatting, and I'll come back on stream. For now, I will leave you with views of the evening here in the giant Niš Fortress Park, looking at the weather station. So stand by for that. Please pardon the camera juggling until that point. There we go. Okay, we're going to try and prop this up. Somehow. There. We still right side up? Okay. So you see anything here? This is just going to be all grass, isn't it? Whoops. We do want it on. Okay. How is the view there?
Just clouds.
Just cloud. Good to know. And now?
There's a weather station behind it for us.
Behind a what? Forest and grass. Okay, how about vertical video here? Pardon the impromptu fun here. Stream, folks. Excellent. All right. Thank you, Martha. I'm going to step off here. A little break before starting the interactive part of the stream. Talk to you soon. Hello, everybody. We'll go ahead and get set up here for the broadcast. Hello, everybody. We are just at the Niš weather station. You can see all the instruments here behind me in the yard. Little classic and new instruments. See the tall anemometers. Here's a classic old one there. If I can get this aimed right. Just over here. So feel free to say hi in chat. Hello, everybody. Welcome to this live balloon launching stream from Niš, Serbia. I'm Dan Bowen, your favorite stratospheric balloon expert. I do consulting for balloon projects, large and small. I help amateurs all the way up to giant international companies whose names begin with a big G, for example. Behind me here is one of only 2 balloon launching weather stations in the entire nation of Serbia. I'm traveling here on the road, and you might wonder what finds me here at a random balloon station in Serbia. And the answer to that is I was just traveling, living here in Serbia for the winter, and on a walk through a city park. And this city park happened to have a weather station in it. And I, um, you know, you run across little anemometers for the Weather Service, and that's not notable. I'm sure you've all seen them around your countryside and so forth. But what struck me as really exciting was this site here behind me. This green thing, this green box, is called a Robotsonde. It actually is an automatic weather balloon launching machine built by Meteomodem, and it allows weather balloons to be launched without any human intervention, any control at all. It's fully automatic. And this is wonderful for national weather services. Check this out. Yeah, we're doing fine. It's wonderful for national weather services because across the world, there are, I think, upwards of 2,000 balloons launched every 6 hours or 12 hours, depending on your launch site. And that means at some places you would have to have staff 24 hours a day, and every 6 hours fill a balloon by hand, tie it to a payload, and open a big garage door and walk outside with it and let it go in the pouring rain or blizzard or beautiful day. So the reason why this was so exciting to me is I have never seen one of these. Only in brochures have I ever come across such a machine. And like, it's top of the line weather balloon technology. So I was just ecstatic. Something happened to the video there. There we go. Just ecstatic. By the way, feel free to drop comments, questions into the chat bar over here, and I will see them and can respond to them. I just need to make sure we're charging batteries so we last through this stream. We're not charging batteries. Is that any better? Is that any better? By the way, the launch will actually happen at 15 minutes past the hour. Here we go, on battery again. It will happen at 15 minutes past the hour. And that is the time that every weather station on the planet will release its balloons. And when you can actually see the number of stations, they're scattered all across the world on all the continents. This particular hour, which is 6 p.m. Universal Time, 18 hours Universal Time, is one of 2 sort of optional launch times in the day. The mandatory ones for balloon stations are noon and midnight Universal Time, but 6 a.m. and 6 p.m. are optional. This particular weather station does opt to do them, as does the other balloon station in Belgrade, Serbia, for additional meteorological data for this region, which is the Balkans, Southeast Europe. This, to give you an idea of the location of Serbia, for those of you not familiar, it is just a few countries north of Greece. It is next to Bulgaria, Romania, Hungary, Czechoslovakia, and so forth around this country. Let's check on this here. So our balloon launch is going to actually happen in about 15 minutes. And afterwards, we will take a look at the results of the flight. And we'll actually be able to hopefully see where the atmosphere's temperatures and dew points were registered. It actually measures from the ground up to about 16 kilometers in altitude, which I think is 45 or 50,000 feet, thereabouts. And that data actually gets converted into a graph, a weather chart known as a Skew-t chart. And this chart allows you to see dew point temperature at different pressure levels and altitudes, as well as wind direction and speed. And those are the values that radiosondes, the little electronic payloads on these balloons, these are the values that radiosondes record and transmit down to the Earth. We'll go take a peek here. We'll go mobile. There we go. We'll go take a closer look at the Robotsonde itself. So, here she is. So, one thing you'll see up here is on near the red light. It's hard to see, but there, just on the right here is a little tiny weather station and a stick. And the weather station is used to calibrate the radiosonde sensors before it launches. So what it does is it looks at this outside temperature and outside pressure and wind, and it actually will then look at the same information from the radiosonde that it turns on before it launches, and actually adjust the calibration of the radiosonde to match. Sorry, this view is reversed. It's kind of hard to handle here. That will match the sensors here on that Robotsonde device. Now the stick that I mentioned, which is just a little white line next to me, that is actually the radio antenna that receives the signal transmitted by the radiosonde. And just that little stick will actually be able to receive the radio from as far away as 100 to 200 kilometers. Basically 100 plus miles in range if the winds are high, which the balloon may be blown downwind by. The other thing that radiosondes collect as far as data is sorry, I'm blanking here, is GPS coordinates. And that's what they use to actually determine what the wind is. The balloon is assumed to be blown by the wind at the exact same speed as the wind. So if you can imagine, the balloon is in the air and it moves with the air. So the wind just carries it along. And so if you measure the speed of the balloon across the ground, we've got an update from our local Met Tech. What's up?
It's okay.
It's okay?
You can film.
I can film? Okay.
Yeah.
These guys, hi. This is Tishan, and he's one of the technicians that record all the data hourly. Is it hourly?
Yes.
Okay, hourly from all of these instruments out here in the field. So thanks for stopping by.
Okay.
It's
Yep.
so this, I'll tell you what the actual box does out here. You can see behind me, oops, maybe, there we go. So the business end of this thing is this white cylinder right here. And the balloon actually inflates inside there from a tiny little folded wrapped piece of rubber up to about a meter in diameter, about 2.5 feet in diameter and then gets released. Well, first, you see there's a little flat cover here, and that is the roof that protects the balloon chamber from weather. And that actually will roll backwards in this direction right before the launch. So again, this will roll that cover back at 15 minutes past the hour, in about 10 minutes. In the meantime, or any time, feel free to drop comments or chats under the video, because I will be able to interact with you, to say hello, to answer questions, or respond to your comments, and it's kind of fun. So again, we are in Serbia, and the Niš Fortress, which is a Ottoman Turkish Roman fortress in the middle of the city of Niš. And we are at the National Hydrometeorological Weather Station, one of only 2 balloon launching sites in the country. And this is the only one that has a Robotsonde, which you see behind me. And this Robotsonde is actually a French design by the company Meteomodem. You can see here, there's an operating door, there's a set of weather instruments, and the white cylinder on top where the balloon will come out later. So in the meantime, we'll take a quick look at the weather instruments here in the field. And it's pretty neat here because this station maintains old and new instruments for backups. And when I say old, these designs are from the mid to early 20th century, some of which have options for clockwork winding mechanisms for their fans even. Fans being fan blades, not people like me. So to just give you a quick tour, you'll see here is a tower anemometer, and it may look standard with the little tiny little cups going around, and there's a little tail, like an arrow wind tail, and a little nose, and that actually rotates around to measure the direction of the air. But this is special. This does not hook up to a computer at all. This actually has mechanical rods that run down through this pipe. It's not just a stand. And those rods are used to drive needles that write on graph paper that turns slowly around as a plot device. A plotting device, not a plot device, though they are exciting. In addition, you might think, oh, well, wind direction and speed, that's what it's for. It has 2 needles, go up and down on paper, great. But there's more. It actually records the air pressure going into the tip of that little vein right here. And it records, I believe, ambient static pressure, which pilots would know about here, which is basically pressure at the side versus pressure at the tip of the wind vein. And armed with the pressure at the tip, which responds faster than the cups do to speed increases, it is able to compare the pressure at the tip versus the pressure at the sides and determine the gusts. It actually uses a tank of oil somehow. I haven't read the manual yet, though we have the manual. And it uses that to measure the maximum gust speed over the last X minutes on another chart. So when you hear a weather report about the wind is 10 gusting to 15, that extra set of air tubes coming down here to the tank of oil would be the thing that was used to measure that gusting. Let's check our time. We're good, another 7 minutes. So here in this field, so many cool instruments. So many cool instruments. We see right here next to us is what's called a Stevenson screen. And this actually houses temperature and humidity instruments against the solar radiation. So it's just basically a shade box to keep the sun from overly influencing the temperature sensors. But this one, these are special. These contain classic mechanical glass mercury thermometers used for maximum and minimum temperature for the day and night, and also for measuring the dry bulb temperature and the wet bulb temperature. And this you might see technicians go up and peek into every so often, at least every hour. And they will open the doors, stick their head in, and then write down on paper the readings they see there. Later on, we might take a look at the manual to that, since I have printed it out. And the amazing thing is, all of these antique style classic instruments are still manufactured today. They still get service, parts, and you can buy them from the company Fuss in Germany. Beautiful German engineering. Some of these are actually clockwork instruments that actually use wind-up gearing and springs to drive the paper drums that get inked by the needles. Actually, oh, we're getting to be time here. Take a look at this. We see. There we go. Which way do I need to go here? And this camera mirroring is more difficult than I remember. Okay, so you should see just to the left of me that there's a little blinking yellow light. And what that means is it is filling the helium balloon. And there's a faint beeping that I can't hear very well, but it is there. And that will stop at 15 minutes after the hour. When it opens. I apologize for this camera work. For some reason, this particular angle is just warping my brain. Good Lord. Okay. So the other thing to note today is we have clouds. We have clouds, and that is exciting because the radiosonde data is used to measure the dimensions, the height, the severity, and the type of clouds. That's one of its primary purposes in life of radiosonde data. And that's something that we will take a look at after the flight, about 45 minutes after the flight. The data for this, oh, I heard the helium just cut off. We're getting very close. So let's go right up close here to the machine. And we'll see this square screen slide off to the right when it's ready to go. And this will be launching a radiosonde of the brand Meteomodem. And the model will be M10, that's Mike 10. It's a fairly standard one from France. And one thing that's exciting is that amateur balloonists have managed to decode the data that gets transmitted by these. And there's now a network of receivers around the world that can decode this information, and it gets put onto a central website for anybody to see where all of the radiosonde balloons are flying at any moment. Now, there's not worldwide coverage for this, but it's extensive for Europe anyway. And depending on my computer access situation here while traveling, we might get a chance to see the data from this. If we don't directly see it live, I will post it online via Twitter or media post later. But we have two cloud layers here today that we'll be looking for on the data chart after it finishes flying. You can see there's a low puffy cloud layer here and those are stratocumulus clouds, just blotchy, darkish, and earlier they represented a little bit thicker threat of rain, and now you can kind of see beyond them is a kind of a white, high, wispy layer. You can see the whiteness behind the gray clouds there. And that is cirrus clouds, ice particle clouds, which are much higher. So on the radiosonde chart, we'll be looking for two temperatures to converge close to each other. And that represents the cloud, or the layer that's likely to have a cloud. And then the dew point and temperature will diverge, and that's likely to be the layer between these two layers we see. And then we will see those 2 points converge again for the high cirrus, and then diverge again on up to the stratosphere. So we should be getting very close to the launch here. And we may lose the balloon in the clouds, but I will try and keep it in view as long as possible. And after this, we'll look at some documentation on what this hardware is. I actually have the brochures for such things. And again, go ahead and say hi in chat. I'd be happy to answer questions, comments, etc. So again, this is live from Niš, Serbia, in the Niš Fortress. Here we go. Here she comes. Look at that, beautiful in the sunset. Beautiful. You can see the payload swinging below it very clearly. And we see it may get shaded as it goes into that cloud layer. This is climbing at a rate of about 5 meters per second, or 1,000 feet per second. And so if we had a timer running, we could actually already get a guess for how high that layer is based on when it sort of shades by the layer. This is great. With the sun so low and the sky dark, we're able to see this balloon for a long time. Oh, that's great. So it is traveling off to the south. Oh, I'm surprised at how long we're able to see this. One of the things that makes this possible to automate is called a derailleur. And that is a device that lengthens the string after it leaves the launch machine, because the electronic sensors have to be like 100 meters below the balloon to avoid getting air across them that the balloon has influenced. And wow, it doesn't seem to be climbing fast, but it may just be the well-lit nature of that. Normally midday, it's hard to watch the balloon. Did I lose it? Oh, it's still there in that big gray puff in the center. It's hard to see it because it's not half lit like this, and the sky is basically as bright as the balloon. So this is kind of neat to watch a sunset launch. So the 100-meter string has to be unwound after launch, because if the balloon launched with the string already extended, that string would drag the payload out of the cylinder and over possibly onto trees and things like that as it swung before the balloon climbed high enough. I don't know if you can still see that. I'm having trouble seeing it on the screen. It is very tiny by eye, so I think it's probably good enough. So we have Flabby says, how many such automatic balloon release machines are operational in the world? That's a good question, and one I don't know the precise answer to. but I know there's only probably, sorry for camera angles. I know there's only probably 100 of these in the world, is my guess. I apologize, Meteomodem, if I'm vastly underestimating your sales reach, but other companies also make these, and I'm not sure of their reach, but there are still by far more human-launched balloon stations than these, and that's because these are very expensive, and they don't completely obviate the need for a human involved in the process, and that's because the thing can only hold 12 to 24 balloons at a time in the queue for launching. Let me put this back on its like tripod here. My arms are getting tired. So it can only accept, like I said, 12 to 24 balloons per you know, per cartridge, and these cartridges are basically a round thing. I have a picture of for you. My high-tech screen sharing here in the field is definitely papers printed at the copy shop. Very old school. So, take a look at this. We see here, this is a 12 balloon carousel cartridge, and you see, my screen went a little off center. You see there are 12 little white flaps there, and under those is all of the things required for a single balloon launch, including the radiosonde, the balloon, the unwinder, and a parachute, which I forgot to mention, because these balloons will climb up to 30 kilometers sometimes, which is 60, 70,000 feet to 80,000 feet, and then they pop, they burst. And after that point, they start falling. And it wouldn't be nice to just drop a random bit of electronics across the land, even if it's styrofoam and the size of a hamburger. The parachute allows it to come down very gently and has no potential of damaging anything. Like your rose bushes would survive the fall on the parachute. It's coming down at like 8 miles an hour at that point, and it weighs like 200 grams. You know what? I know how much it weighs. Because I have that leaflet too. Oh, who else do we have here? Did my chat? Oh, there we go. Hi from France says, oh, it's Ilan. Am I saying your name right? Ilan Raphael? Hi from France. Thanks for the stream. Very cool. Do you know why such small balloons are not inflated using hydrogen, especially when launched by a robot? I know. Robots are cool with hydrogen. This would reduce the cost and environmental impact of the launch. Yeah, I do. And it is the same reason why most it is the same reason why helium balloons are inflated with helium generally everywhere instead of hydrogen. There are balloons that are inflated with hydrogen that are widespread, and in fact, I think most weather balloons are flown with hydrogen. But these are for the safety. This, as happens in history many times, there have been accidents with hydrogen, and they had a small incident in the 90s that led them to decide to lean towards the safer, just in case side to prevent any actual injuries or anything like that in the future, to do it with helium. Though these Meteomodem Robotsonde devices are fully capable of hydrogen, and it remains ready to do hydrogen at any time if they ever decide to switch back to hydrogen. It's ready. Like all hydrogen requires in general with gas handling for balloons is as long as you choose the right material in your tubes and pipes to be hydrogen compatible, then it's automatically helium compatible. So The only thing that needs to be changed if you actually switch from hydrogen to helium or vice versa is the connector to the cylinder is different, and the regulator usually is different as well. So with with probably 30 euros of parts, you could swap if they don't already have both sets over to hydrogen. So I was going to show you here we have the specs of the radiosonde. I don't expect you to be able to read those outright, but I will scroll them ever so slowly here. And this is the actual device that flew today and is still flying as we speak. The weight of this radiosonde is general weight, 150 grams, which is about what I guessed. I guessed 200 grams, but the unwinder and valve and parachute probably add another 50 grams. So I would guess you could assume a 200 gram payload for these flights. And for you amateur balloonists out there that want to calculate the predicted flight path, the balloons they use here are 500 gram Totex brand balloons. If you go to habhub.org, that's habhub.org, maybe .uk. I apologize, guys, for not remembering that URL, but just search for HabHub. There will be a burst predictor and a track predictor. I can't remember the name. It's been a while since I've launched amateur balloons. And with that, you can plug in the 500 gram balloon Totex and the 200 grams of payload and the time of launch in this location, which is Niš, Serbia. And it will produce a burst altitude prediction, and then you can plug that into the map tracker where it will predict where the burst will happen based on winds predicted, and then where it will land based on an assumption of your descent rate, which without the exact parachute model, we don't know the probable descent rate. So let's see. This is a picture of the actual radiosonde. You can see someone holding it in their hand. It's about the size of as you say, probably 10 centimeter cube, hamburger size, basically. There is a couple better pictures of what's inside this robotic radiosonde launcher. Tip this up again. You can see this. So here's the flyer. I apologize for low res if it is not legible. You can see these two launching photos, and the more interesting bit is down here. If I can hold with two hands, you'll be able to see. Down here on the lower left, we see a carousel with more of the bits and pieces in it. So we see up at the top is a parachute. Actually, is that a parachute or a balloon? Yeah, definitely parachute. Yep, okay. So it looks like we have the red parachute. The white thing is the radiosonde itself, the Meteomodem M10. And under the white flap is probably the balloon, which is attached to a one-way valve in the neck of the balloon, which sits on a nozzle. And around the balloon's neck is a solenoid electric-driven clamp that holds it down onto the filler nozzle until ready to launch. And the balloon's neck is a one-way valve that actually flies with the system. So when the clamp releases, the rubber neck and the valve pop out and fly up away, as we saw. What else would be interesting for you all to see? So again, here's another picture of a launch event. You can see there's the balloon with its red parachute coming out of the hatch. And here we see what's inside the door. I know if you're like me, you're desperately curious what's inside that white door. What does it look like in there? This. So you see that big white cylinder here. That's the bottom of the cylinder that we see over here. And that is normally behind this sliding door to keep that chamber temperature and pressure, climate controlled. And then here we have just simply, the control computer and whatnot. And around the rest of the room is just like storage bins and stuff like that, just cabinets. The room's about 2 meters by 2 meters. So let's take a look at the data that comes out of these. So this is the data that gets recorded after the numbers come down from the device in the sky. Let's see if I can get to one side or the other here of this. Sorry, the camera angle's a little weird here. This tripod is a little lower than normal. So we see here this, I'm gonna go bigger screen here, so I will see, we'll lose your tweets off screen, but let's see, make me bigger. How do I make me bigger? Oh, we might have Mike here. Hello, Mike, are you there? Leave him tiny. But my brother Mike might join us. Did I get that right? There we go. So it's a little bigger here. Hello. We have my brother Mike Bowen, who is in the USA in South Carolina. How are you doing?
Excellent. Looks like a beautiful day there.
It sure is. The temperature, I could ask these guys what the temperature is, but it feels like about 18°C, like 60, 62 degrees out. It's kind of damp, but you can hear the crickets are beautifully chirping. It's getting darker. It's 7:30 p.m. local time. You see we have this is the chart that you get after the data comes down from the radio sound. It's called a Skew-t chart. And the reason for that, I believe, is because the temperature is on diagonals and not straight vertical grids. I will just do a brief explanation of this chart because it gets pretty academic quickly. But vertically, this is altitude. And these diagonal lines are temperature. So the temperature numbers are at the bottom, as you see. But they represent, like this dark orange one here, 0°C, represents, like, this is 0 here, as well as this. So you read that black line, which is the actual temperature that gets recorded. You read that along these diagonal lines. Sorry, weird angles here. The other line is the dew point temperature. And that is very important because that is what tells us, a comparison of that versus the black line is what tells us what the clouds are going to be doing. So today, this you see, I downloaded Friday, May 14th. Today's sounding we can expect to be available around 25 minutes from now, maybe 20 minutes. That is something we're going to try and see. Maybe Michael could help us. I'll send you the URL a little bit later, Michael, if you're going to be around for the computer. We could share that PDF. So what you see here is as dew point creeps close to temperature here, that's where clouds will be, or very likely to be in this region here. But as the dew point creeps away from the temperature, that's where the air is a little drier. The relative humidity is lower. Where they get very close, that's where humidity gets higher and higher, 90% humidity and so forth that you experience during precipitation, a storm, etc. So this was Fridays. And here's an example of the chief meteorologist here of the weather station. I've gotten to know the tech, and one of the techs here and the chief meteorologist at the Serbian Hydrometeorological Niš station. And he very graciously shared some cool examples of graphs that they have gotten from this station's balloons. So this one, you'll notice, looks different. The black line, hey, I can do two side by side. This one, you see the lines are very close, or a very long ways from bottom to top, whereas this one is zigzaggy and farther apart. And what that means is there was a freaking huge pile of clouds. And the way this is smoothly following together means that they aren't storm clouds. They're not boiling and roiling like a thunderstorm is. What that means is it's a very calm atmosphere that's just wet. And those are the days when you have a solid cloud deck, just a gray overcast, maybe light rain. And for pilots, the base of your cloud would be basically ground level. See how close they are. And would go all the way to the tropopause. Shit, that's basically up to airline cruising altitudes. It's possibly socked in with clouds. An IFR day. So that's pretty cool. And this one is an example of a bad day. A very bad day. As you could probably guess by this red splotch in the middle, something's going on. It's a potentially bad day. In fact, it didn't turn out to be, but what the red means is that the atmosphere's temperature is basically wrong. Normally, the temperature from down here to around up here should always go in this direction. It should always get colder until about here, where it should get warmer, which you see perfectly following with this one. Beautiful demonstration of this is the lower part of the atmosphere, the troposphere, and this is the stratosphere. And the dividing line between troposphere and stratosphere is by definition where the temperature starts changing in height. So here the temperature is getting colder and colder with climbing altitude. Then all of a sudden it starts getting warmer and warmer as you climb higher. And that knee, the inflection point, is the dividing line definition of stratosphere and troposphere. And the name for that line is tropopause. So what you see here is some glitches, particularly down at the bottom. You see the line is not smoothly going to the left. It's not a smooth left diagonal on the black line. See, there's little overhangs, little hooks in here, little hooks. And you see several little ones here as well down the bottom. And those are temperature inversions. Like I said, that's where the temperature sequence going up reverses. It gets warmer for a minute and then starts getting cold. And that's generally what causes smog to stay down low, if you have a big one of those on like a summer day. And that's what often causes storms. If you have enough water in the air and there's one of those little inversions, one of those little hooks, you will get precipitation and what they call an unstable situation, unstable air. And it's not just like the computer obviously can tell when there's risk of that. This particular day, you see the dew point didn't support huge storm clouds. The dew point, there was only enough moisture in the lower air to get nasty a little bit. So there's probably some rain because the dew point was so close and the cloud was under the little hook. So that basically makes it at a risk for dropping moisture, condensing. So you don't have to just read the line to know that there's a risk of this. You actually get a number. The CAPE, C-A-P-E. It's probably very blurry, but this one says 1974 joules per kilogram. And indeed, there's a little zigzag, probably looks like a chevron. It's a lightning symbol. So this was probably a mildly stormy, maybe lightning-y day. And this is unusual to see this much of a huge potential for instability. So that's why they showed it to me. It was notable. It was pretty cool to see. So let's see how we're doing on viewers. Hey, we still got 3 viewers. Again, you guys feel free to say hello in the chat. Just checking everything's still working. And Michael, I will send you the link here. How can I do that? I can use my other phone. These broadcasts require 2 phones, one for broadcasting, one for having a data plan. Speaking of which, I should plug this one into power. While I'm looking for this, does anybody have any questions out there? Got the link. You see this really cool antique weather station setup. So it's pretty cool. The Serbian government.
Does the payload ever get recovered?
Say again? Say again?
Does the payload ever get recovered? Is it postmarked or?
Only by amateurs. The government. The government does not recover them. They are just labeled as like, hey, you can dispose of this, recycle it, or mail it back. But now, in the past, 5 years or so, amateurs have figured out how to locate them when they fall, because they still transmit all the way to the ground. And using the GPS coordinates it reported last, you just drive there and go drag it out of the tree, and you've got yourself a high quality temperature humidity sensor and transmitter for location. Amateurs have used these like legally by changing the frequency out of the weather balloon frequency band. And that's important because otherwise they would interfere with government data during flights and it would be illegal to operate. So amateurs usually find 400 megahertz radio sondes and use various methods to shift them up to the amateur frequency of 430 megahertz, which is really cool because sometimes it's expensive and complicated to build a balloon tracker. And when you do that, it's nice to have a backup tracker on board in case something happens to your prized main payload. I'm gonna get a coat on it. I'd say it's getting colder. Let me see. Yeah, it's probably 17 C here. So Michael, I Facebook messaged you 2 links. Try screen sharing from the computer. Michael is so graciously hosting my sort of stream central control on his computer, as it's been kind of difficult to juggle all the the needs of a stream while I'm in the field and traveling. By the way, it'd be wonderful if you could consider helping me out to support these streams and other educational balloon content with your donations at patreon.com/balloonscience. These streams out here in the field are kind of expensive. It costs about $10 in data every time I do a 2-hour stream in this region here. And we've got hardware costs, like I have to keep a tripod in good repair here while traveling and things like that. This kids' tram driving by in the park here. By the way, this Niš Fortress is huge. It's 80 hectares, which feels like about 50 acres when you walk around it. So Michael, go ahead and open those links in a web browser on the Mac Pro, if you could. And there's a button below the preview stream on this web page that you see a little red slash through a laptop, which is screen sharing. So what I'm hoping to show you is the website that releases the Skew-t chart, and also possibly the website that tracks these live, tracks our balloon live if the amateurs network is receiving it in real time. In the meantime, I'll give you a little walk here around our weather instrument field. We're not going to go into these in super detail tonight, but we can probably see the anemometer in a little more detail. I'll go over this side. And there we go. You can see here, you can sort of see how it's kind of chunky compared to the modern sondes. Oh, now it's in the dark, but you can see the silhouette. So you can see the little cups and the vane, the wind vane there. Pretty sky, huh? As we walk around, there are 2 of those Stevenson screen little houses, as you can see. Let me close the chat to make a little more wind, more view. And there's a white box in the middle, which is taking dust samples with that big fan rushing noise. And we see a modern Stevenson screen equivalent here. This little horizontal slats cylinder in there. Same thing, just a sunshade with vent rings around it. And on the left is a pretty cool device called a radiometer. It's a little cone, little flat cone. Looks like a security camera upside down. And that measures the total solar energy that comes down to the ground, which is one of the core things that is needed for determining what weather might do in the near future. This is a snow and rain gauge collector. And there are several of those. You see here's a modern anemometer and wind vane, a little smaller instruments than the antique one. And go around here. See, one of the techs is, you can see his legs there doing the reading in the Stevenson screen. And what else do you see here? Oh, this is a cool little instrument. This is a very old classic rain collector, rain gauge, and it doesn't just collect rain in a marked, bucket like common ones might, but this one actually uses a clockwork mechanism again to drive a little paper drum, and the rain fills a little cup, and when the cup tips over, it records that increase in amount of precipitation on the drum. So it's actually a clockwork wound mechanism. So thank you, Michael. We'll take a look at those when I finish this walk around. So this is a beautiful, fascinating little instrument here on the pole. Let's see if we can keep your eye on that. You see there's a glass sphere in the middle of that. It's kind of hard to see, but it's got two little metal horns that kind of wrap around a glass sphere in the middle. And what that's for is those horns, they have a piece of paper that sits inside of them. And every day, the sun, a new piece of paper is put into those horns, and the sun will burn a track all the way down the paper. And when there's cloud, there's no burn mark. When it's sunny, there's a burn mark. And so you can account for manually the amount of solar radiation generally, and how much cloudiness and when there was cloudiness generally in the day, which is such a cool manual but simple way to do that, isn't it? And here again we see the tech reading the Stevenson screen. This is the glass thermometers. So Michael, why don't you go ahead and click the screen sharing button. Let's see if you're in there yet. And pick that window, the browser window. Oh, I plugged my phone in. Oh, yeah, see, you're getting it. Hey. So if you would, go ahead and zoom that window down to Serbia. You could drag it so that it shows to the lower, where am I? There I am. Yep, go down south, right next to, oh, you've already got it clicked. Yeah, zoom into that red one down there. And let's see where that came from. So that's the Belgrade radio sonde. See how that line comes straight out of Belgrade? That's the other balloon launching station in this country. And if you scroll down just a little, yeah, should be a 3-letter city. Stop. This is, oh, there you go, Niš. Yeah, scroll it up just a little bit more. There we go. So that is where our balloon launched, and it is not being picked up at the moment. That means probably we aren't going to get the signal from it if we haven't picked it up yet. Thank you, Michael. That's great highlighting. So in the meantime, it's getting close to the top of the hour, which is the time when the balloon's data might be published. So let's click over to the other tab. And we see the second PDF link there will turn to an 18 UTC when we get the latest data. So we can take a look at the 12 while we wait and see if we see how we compare the two soundings. Whoops, sorry. I think I'm accidentally showing chats. And feel free to say hi and ask questions in the stream. Okay, yeah. So can you click the little menu dots on the left to widen that up? Yeah. Okay. So also narrow the window, I think. I think that'll give us more vertical space. Down to 20% battery. Okay, yeah, that's good. Actually, let me turn the chat down. Give us a little more detail. Okay, so this is the sounding from this site today at noon UTC, which is 1 p.m. here. This is 6 hours ago exactly. We see that the temperature in the black line there on the left was fairly consistent, but you see there is a little hook halfway up the screen right there. Yep. And you notice that the dew point has jumped up right next to it there. And that indeed was a cloud at that layer, and possibly a rain cloud. And indeed, I think we did have a few sprinkles today. It's not huge and it's not red, so it's not vertically very long, and the dew point isn't right up against it. And that's probably why we didn't get much of a cloud there. But you can see the atmosphere is fairly wet. The dew point is moderately close to temperature from there to the ground, so it's kind of damp. Now, we don't see, what is that height? I can't quite see at that hook there. That, can't hear you much. It is 4 kilometers, 4 kilometers. Okay. I'm not sure if that is this cloud deck. Honestly, this looks lower. Like this cruddy stuff, see how detailed it is and puffy? It usually means it's closer to the ground than 4 kilometers. I would guess. The tech earlier said one of the readings put it maybe around 1,000 meters, which is 1 kilometer. So we see, yeah, let's look at the top of the chart there. Dew point temperature remained very far apart, which means, again, no clouds in the stratosphere, and there's usually never any. Let's look at the little box up the top, the key. Oh yeah, so troposphere, it was a very gradual turn of temperature. It's not a real huge definite knee in that chart. So the computer estimated it there, but if you scroll down a little, yeah, it's probably more in the shallow part there, maybe, which is 10 kilometers. Yeah, 10 to 12 kilometers is very normal for the troposphere boundary. And you see at that boundary, the top of the troposphere anyway, there can be a lot of wind. And you see that barb there has a heavy triangle and four extra barbs, yeah. Michael, do you remember what the barb increments mean? I can't hear you. 10? Okay, yeah. So it's the big triangle or the 50 for the flag, damn. Okay, so we're talking 60 knots wind at the top of the troposphere, which is pretty standard, basically jet stream type speeds. Let's go ahead and go back with the browser and see if we can reload the... Oh wait, before you do that, look there, the CAPE, it says 0 joules per kilogram, that black text on the left there. And that means it didn't predict any precipitation, no like storminess, but it did predict 3.4 millimeters of rain, which is probably to be expected from a thin, just a thin layer of clouds that weren't in a huge inversion. So let's go back and see if we can reload the page. Yeah, reload that one too. See if we get any update. Anything? Hey, look at that. We've got a balloon. We have a balloon. So go ahead and click on that purple balloon there. And go ahead and zoom that map in a little bit. Yeah, so we see on the left, can you Apple Plus the screen about twice so we get bigger text? Or Apple equals, whatever, the enlarge. There we go. Click the question mark in the upper right. The far top right. In the blue header. Question mark. Question mark farther right. Farther right. Keep going. It's up in the corner of the blue. There we go. Thank you. So we see on the left, the black text is our balloon. And this gets updated fairly frequently, 55 minutes after, a couple of minutes old, but that's fine. So we see it was last climbing the top line of 4.8 meters per second. I gotta turn this around, my back is killing me. Climbing at 4.8 meters per second. Altitude is 12.2 kilometers. By the way, on the top line, the first number, 4.8, is speed vertically, and the second number is speed horizontally. 30 meters per second is sprightly. Let's find out what that is in miles per hour. What is 30 meters per second in miles per hour?
That would be 67.11 miles per hour.
Yeah, sporty. 67 miles an hour right now at 12.2 kilometers, which again, around the tropopause, is probably normal. The battery we can see on the fifth line, 5.6 volts. The frequency, 402.4 megahertz. That's different from yesterday. I think we had 402.2 megahertz yesterday. It's curious. Humidity is 16%. Down a couple lines, we see temperature is negative 56. And the Radiosonde brand model is M10 Meteomodem. Let's go ahead and refresh this page to see if we get an update. This site doesn't always auto-refresh yet. They're still in the programming testing phase of this. And you can actually click, Michael, on the there's the third line down on the left and the white. There you go. You got it. That's our song. So latest update was 2 minutes ago. Let me see my screen now. That's better. Now I can see it. Same rate of ascent, same horizontal speed, 4.9, 30. Altitude is now 13.1 kilometers. And you see on the altitude line, the altitude is repeated twice, 13.116 meters. The one in parentheses is the maximum altitude recorded. So if this bursts and starts falling, the parentheses will tell us how the maximum height was. So going down, our battery voltage is similar. Humidity has dropped by half to 7.6%. Temperature is similar at 56 degrees. So if we had this data all the way through the flight, we could plot that temperature and humidity and build that chart that we were looking at earlier, the Skew-t graph. Not sure what that does. I think that's just varying from here to there. So you see on the map that each of those balloons has a dark colored track and then a faint track. And the dark color is the recorded path, and the blue is where it would fall, and then the little target is where it would land if it burst right now. So this balloon has already reached the Bulgarian border, which is the gray line there. And so it will undoubtedly land in Bulgaria, south of Sofia somewhere. And we see the red balloon towards the top, which is the one launched from Belgrade, the other station in this country, which is at very similar altitude. And let's see, their temperature is 54, humidity is 3.5, even lower there. And if we zoom out a little bit more, these balloons, they're so high up that they can see the horizon as far as can be seen from these balloons at their altitude is the blue ring. So right now, the balloon that we saw lift up out of the robot can see almost Athens, Greece, almost to Istanbul, and it can right now actually see Bucharest, Romania, Sarajevo, Tirana, huge area, like the whole Balkan region almost already. And that will just get bigger as it climbs higher to see farther. It's helpful to know that. because that can tell you a guess of how far away you might hear it on your radio receiver. Because the radio at 400 megahertz is similar to the distance that can be traveled by light. It's an awkward way to say that, but the radio visible and visible horizon are similar. Yeah, if you see down there in Turkey, actually Syria, Jordan, Israel, those balloons have already reached their apex, being one of all of these launched at the same time. They are already on their way down. One over Damascus there and Jerusalem. If you zoom out and show all of Europe, yeah, you see that one is down to 4 kilometers, almost to the ground. You see all the little green towers are amateurs who receive the signal. And holy moly, are there a lot. If you click on the gears in the upper right, Michael, you can turn off ground receivers. There we go. So now every balloon here you see is in the air right now. Every one of these. And they were all launched at the same time as ours. Isn't that fantastic? Fantastic. See, these haven't gotten to their parachute falling phase yet. Look at that. Look at that. It's pretty. All over Europe. So this is possible. Hey, Elon. Good to see you. Thanks for hanging out. You're welcome. And likewise, thank you for sharing. Elon runs the Balloon Archives Twitter account, and I run the @BalloonSci Dan Twitter account as well. So great to see you. We should chat sometime. Take care, Elon. Sorry, navigating on the phone to control the stream. The stream is tricky. Cheers. Here we go. So Elon is at Balloon Archives on Twitter, and he posts great pictures every day of historic balloons and scientific stuff, balloon stuff. Here we go. So let's take a look at ours, Michael, how ours is doing with the latest telemetry is. So we've got, yeah, we should reload the whole page. It's not updating in real time. So this is cool. This is amazing to me. So cool that we can watch a balloon launch here in the middle of the Balkans and watch it on a map where it flies. I'm thinking of buying some of the decoder equipment here, maybe going and chasing one of these balloons and finding it and picking it up. Believe it or not, the radio hardware required to receive these and decode them for this map is available cheap in Belgrade. There's an authorized reseller of RTL SDRs and MySonde Go devices, as well as Raspberry Pis. So our latest data, we're at 15.3 kilometers, 5.5 volts, 0 humidity, negative 55 C temperature. Now I've noticed on the amateur site that humidity goes down to 0% when it reaches the stratosphere, which is in proportion correct. The stratosphere is extremely dry, drier than the driest desert on Earth. And the sensor probably, it's possible the sensor is not able to read such low humidity. Oh, hey, telemetry. Nice find. Let me turn the banner off so we can see that fully. Where's my banner? There we go. So what do we have there? We have predicted altitude Oh, it's I don't know how you would. Oh, you know what? Just start at, see the light blue area on the left. Drag select over that whole area. Just the blue. Yeah, there you go. A little farther to the right. A little farther. There we go. So go ahead and click the question mark in the upper right to get rid of that banner on the side. And yeah, let's look at the chart. So this chart shows the temperature. The external temperature has been oscillating a little bit over the past. This is about 15-minute long graph, and our humidity has been rising slightly. That may not be percent. That may be just a raw value. Altitude shows. Oh no, humidity is the gray line. It is indeed descending there. Nice, smoothly to zero, as we would expect to basically be at the bottom range of its sensor when getting to the stratosphere. Very nice find there. So let's reload the other page to see if we have the sounding diagram, and we'll look at that and then wrap up for the night, I think. So just reload that. Oh, nothing. Maybe shift reload. Oh, you know what? It has to get up beyond like 16 kilometers before it will produce the chart. So we're still, I think, just below that. Yeah, 15,388. It'll probably be another 5 minutes, 10 minutes before we get the chart output. But I appreciate you all hanging out here with us. Michael, I really appreciate you driving things in the back end. That makes, you know, this part of the show would have been off without being able to do the live web viewing. I really appreciate that. By the way, before we wrap up and look at the data, I would like to thank my patrons, Mike Bowen, my brother, thank you, Sheila Bunch, Ben Lathan, Ken Howard, Sophie Searcy, M. Fong, Ashley Meyer, Robert Quattlebaum, and Steve Randall for financially supporting my balloon science education outreach for everybody. I really appreciate it. You too can donate at patreon.com/balloonscience, and it's very helpful. I have to be very careful on the phone to not hit the wrong button. There we go. Do-do-do. Any chats? We don't have any chats. So we currently we're at 16,800 meters, 16.8 kilometers, 5.5 volts, negative 55 degrees, and still zero humidity. Oh, nice. It shows along the path with a little red marker as you do telemetry. So the chart looks like it is updating. That's great. That's great. Let me make sure we get a better view there. Yeah, that's nice. How did you zoom out on that? I never figured out how to zoom out. Humidity just spiked. I have a feeling my visual is getting dim. It did. That's probably an error. How much spike did it do? Probably an error, but and we probably can't see that on the output chart. It's above what it measures. It's probably an error, I'm guessing, but I don't know. We'll see it further data points. That seems a little excessive of a spike in such a short time. particularly in the stratosphere. It's not like we're going to encounter a cloud deck on this kind of a night unless there's a giant thunderhead blasting moisture up to 60,000 feet. We shouldn't see moisture like that in the stratosphere. .8 kilometers high here, and we are into Bulgaria already. Altitude is tracking predicted closely. Oh yes, that is one thing that is fairly good at balloon math, is fairly good at predicting is the altitude over time. But it's not simple. Like there are it's not entirely simple math because some balloons just behave differently than quite expected, and it's, I think, generally due to the way they're shaped as they climb, the way they oscillate and flap and so forth. But those factors usually get taken into account now that balloons are very consistently built, and the dimensions of each are nearly identical based on the manufacturer and the mass of the model of balloon chosen. So we're now at 17.8 kilometers, solid 5 meters a second up, 5 meters a second horizontal. That means we're going 20 miles an hour sideways. We've slowed way down. And the humidity is 0 and temperature is pretty constant still at -55. So this balloon is still climbing. So let's go ahead and check for the Skew-t chart again. I know this balloon is probably going to continue on up to at least 27,000 feet, so it's probably going to go another 20, 30 minutes for its flight. But I don't think I have that in me. Nothing. Oop. Try shift reload. Maybe. Nope. No joy. Well, we'll go for another 5 minutes, and if it's not there, we'll wrap up. So this type of system, anybody can buy the equipment to receive this data and have it upload automatically to this website. And it generally is a Raspberry Pi and a software-defined radio USB dongle. It's about 30, 40 bucks. So we got another data point. We're at 5.5 meters per second up, 2 horizontal. It's slowed down. Look at that little swirl that it might follow if it falls based on predicted winds below it. We are 0 humidity, -57 C, 18 kilometers high, crossing the border. It's really fun to go chase these in your car, etc. As you can probably tell, I'm just lit by my phone screen. Did you have any questions, Michael? No worries if not. Just relax here for a little bit. Still 12 UTC. Yeah. Last night it came out right on the top of the hour, which was, I thought, pretty unusual to come out so fast. It's a nice night out here. Park is open 24/7. It was built, I'm just kind of guessing, but generally it was built by the Romans, I think, maybe year 300 or something. I think it was mostly built out by the Turks in like the 1600s. What about the unwinder? Yeah. So the unwinder is a neat little device that it's made of plastic, and it. Let me just do a different view. So the unwinder device is pretty neat. It basically allows the string to be wound in a very special way around a tube or a special shape in plastic or cardboard. And what happens is it's attached directly at the balloon, and it takes advantage of the fact that the balloon has mass and therefore inertia, so that when the string falls off one edge of the little, say it's a little triangular shaped piece of cardboard, which sometimes it is, the string falls off one side, it tips the balloon bottom this way, but the balloon takes a second or two to come back this way, so the string is kind of hung there, falls off, and then it's kind of caught here for a second, and then it falls off this side, unwinds, and then falls up this side and unwinds, and then falls up that side. So what ends up happening is the balloon rocks back and forth as it climbs, and each time it rocks, it drops another 2 inches, 3 centimeters of line off. And the reason why it takes time is that the balloon takes time to rock, probably about like this as it goes up. And they just wind 100 meters of basically dental floss on that winder. It's something that amateurs really haven't used much, but would really benefit amateurs to a great degree, because it's very common to have a long rope or long string for your payloads below the balloon. And without the unwinder, if there's any wind at all, you have to lay the string out on the ground as long as the string is, with the balloon and parachute and your payload, and that might be like 10 meters, like 30 feet from end to end. And it brain blank. Right, so when it launches, if there's wind, you have to make sure the wind is coming from the balloon towards the payload, so that when the balloon stands up, it takes the string with it like this, because the balloon doesn't rise instantly. It doesn't get up to speed instantly. It accelerates slowly, and at the same time, it's moving. So you end up taking basically a diagonal trajectory, and then it lifts up your parachute, and then it lifts up your payload, and you take off. But if it's the opposite way around, if your balloon is here, and your payload is here, the balloon and the wind is blowing this way still, the balloon will rise and then go away. Like it will want to rise and go downwind. Whereas your payload, sorry, I got my arms crossed. This is crazy. Your payload here would drag along the ground as the balloon took off. So your balloon here, your payload here, would drag the payload on the ground and damage it and so forth. So anyway, with the unwinder, you could have the balloon right over the payload, and they both launch at the same time and slowly start spreading apart in the air, taking 30 seconds to a minute to fully deploy. So yeah, how are we doing on this thing? Let's take a look. Michael's showing us. We're 19.9 kilometers. negative 57 degrees. We're still hovering at that border because the speed is very low. We're at 4.5 meters per second horizontally, so it's just kind of hanging out there. It's interesting. And it's a fairly mountainous region, as you can tell by all the zigzagging roads and things. I think it's very mountainous. Possibly the Serbian Carpathian Mountains, which is a great name, I think. Zero humidity as expected. No data? No data. Okay, we'll wrap up the stream. Michael, thank you so much for helping with this. Again, let me flip our screens around. Still got screens. There we go. Again, thank you so much for coming out, everybody watching. I'm here in Serbia, traveling a little bit, just trying to live here. And these wonderful people at this weather station have allowed me to hang out in their yard and watch their cool stuff going on. It's been really fun. They've been wonderful people, the chief meteorologist and the technician, just fantastic. And I'm so excited to see balloons on my travels. I didn't expect to, and I've missed balloons. So everybody, feel free to subscribe on Facebook, Instagram, and Twitter at Balloonside Dan. So take care, everybody, and have a great day.